All right, so we're going to jump through this worked example of this logistics question. Some of you tried this and got a little bit stuck and it didn't really make a lot of sense. Let's jump through it. We're going to jump through it in a much, much easier way than probably what the textbook explains it, or at least I hope so. So a population exhibits logistic growth using this function, and at time 0, the population is 100. All right, solve for NT by using the logistic equation directly. Now, part A is really, really straightforward. You've got the function that they've given you. Change in n with respect to t equals an, so a is equal to 1, and b n squared, which is 0.002. Now, you might make a mistake here by thinking that b is equal to negative 0.002, but there should pretty much always be a negative there. So b doesn't refer to the negative of that, it's just whatever that is, 0.002. All right, so this is something you pretty much have to memorize because we're subbing that directly into the logistic equation. That's the logistic equation. So really, you just need to memorize the logistic equation. It might appear on a formula sheet, but probably not. And then you're subbing in A, B, and N0, which in this case was 100. Sub it all in, and we've now got a function 500 over 1 plus 4e to the negative t. And that function, if we drew it, would look something like this, where that's 100, the limiting population is 500. That shouldn't be curved, that should sort of head off. Not very good with that style. And then you can see that our maximal population is going to be about 250. Not really answering part A with that, just giving you a feel for what that equation would look like. Part A, super duper easy. Part B is where we got stuck. Verify the solution by differentiation. So let's jump over here. Now, I did talk about this in the previous video. We know that the change in n with respect to t is equal to n minus 0.002 n squared. But it's not great because that function is in terms of n. And when we've got a derivative function, we really want it in terms of t. We really want it in terms of the thing that's on the bottom of that of this thing here. So all of the complications arise from that fact. If it was in terms of t, then this would be a no-brainer. We'd just anti-derive it and we'd be fine. Okay, so we can put it in terms of t in two different ways. If it works both ways, then we've verified our result in A. So what I would suggest you do is kind of work in your book like this, and we're aiming for two similar results here. Here, so you can see I've got my two similar results, so I've verified using differentiation. All right, so first way is the obvious way, derive NT that we found in part A. So we had NT here, so if I find the derivative of NT, then I'll have the change in n with respect to t. So NT from part A was 500 over 1 plus 4e to the negative t. So the change in n with respect to t, you've just got to derive that using the chain rule. Now, if you have a little bit of trouble with it, you can come and talk to me about it. But basically, you can, what I've done is take 1 plus 4e to the negative t, moved it to the top as 1 plus 4e to the negative t to the power of negative 1. And then I've replaced that with u, found the derivative of 500u to the negative 1, found the derivative of 1 plus 4e to the negative t, and multiplied them together. All right, so your derivative should be 2000 e to the negative t over 1 plus 4e to the negative t squared. All right, that's probably the easiest part of this. The next one is just maybe a little more complicated. All right, so the second way is not so obvious. From the question, we know that the change in n with respect to t equals n minus 0.002 n squared. And from working in part A, we know that n anywhere is equal to 500 over 1 plus 4e to the negative t. So we've got a derivative function which is in terms of n, and we want it in terms of t. So if we know what n is, and we do, 500 over 1 plus 4e to the negative t, we can take that, sub it in for n, and then we'll have the derivative function in terms of t. All right, so, and this is really pretty straightforward. I've subbed it in for n there, I've subbed it in for n there, I've squared top and bottom, I've added the fractions by multiplying this one by 1 plus 4e to the negative t, top and bottom, and this is my answer in the end. Now, because they look the same, I can say that I verified this solution by differentiation. I verified this one by differentiation because I took it, I differentiated it, but then I also took the derivative function with respect to n, and I did it in terms of t so I could directly compare them. So that was part B. All right, pause it, take a break. So the next question is solve for nt by applying the integral calculus. So it's not overly difficult, but it is really kind of tedious. You can see how long part C is there. What they're asking is, you knew that dn dt equals n minus 0.002 n squared, and they're saying solve for n. You can't obviously just come up with a function for n like by deriving it directly, but we can rearrange it, and we've done this a few times now, where n's are on the left-hand side and the t's are on the right-hand side, and then we take the integral of both sides. So in one single step, you should be able to get from there to there by moving all the n's to the bottom, integral of the left-hand side, integral of the right-hand side. Now, this is probably an optional step, but it probably does make the working a little bit easier. Just by multiplying the left-hand side by 500 over 500, I just eliminate the 0.002, and it becomes a neater 500 over 500 n minus n squared. And then I'm just factorizing that bottom. Now, it came up in my explanation in the last video, but it's time for some partial fractions again. Because you've got 500 over n times 500 minus n, and you want to find the integral of it. So this is a classic case for partial fractions. So it's going to be sum capital A over n plus b over 500 minus n, multiply a by 500 minus n, multiply it by that, multiply b by n, that's an n, not a weird w, over, and then it's n times that. So we know that that is equal to that, which means that 500, the numerator of that, is equal to the numerator of that. So 500 is equal to a bracket 500 minus n plus bn. And then you just sub in 0 for n, sub in 500 for n, and you'll find out that a is equal to 1 and b is equal to 1. Therefore, the fraction that we started with, 500 over n bracket 500 minus n, is equal to 1 on n plus 1 on 500 minus n. Okay, so all of that is kind of a bit of a sideshow because we started here at 500 over n 500 minus n. The integral of that with respect to n is equal to the integral of dt. So now we can take the partial fraction we just found and put it in for that fraction instead. So now we have the integral of 1 on n plus 1 on 500 minus n with respect to n equals the integral of dt. Find the integral of this. Now, you're going to do this pretty often, and a lot of people have asked me for this negative here. The negative comes from that negative n. So the integral of 1 on 500 minus n is negative ln 500 minus n. And the integral of that's just going to be t plus c. Now, you know there was a plus c on the left-hand side here, but they're two different plus c's and they're arbitrary constants, so we can just group them together. But we need to know what C is, but we do have a known point. We know that when time was equal to 0, n was equal to 100. You can find that just in the question up here somewhere. All right, so subbing in that point, we find out that C is equal to the natural log of 1 on 4. So here's our new function, ln n on 500 minus n equals t plus ln 1 on 4. And then you've got to know your log laws here, minus ln 1 on 4. And then I've grouped those to be ln 4n over 500 minus n. That's because it's subtracted, so it's going to be this divided by 1/4. I'll leave you to play with why n over 500 minus n divided by 1/4 would be 4n over 500 minus n. But that really should be like a single step. You could probably add an intermediate step if you had to. And then we've just rearranged it. So by taking the reciprocal here, we'll get negative t. Again, you can kind of play with that a little bit, but one way to do it would have been to go back 2 steps, make negative t over here, and it would have been ln 1/4 minus ln n on 500 minus n, which would have had the result of flipping that. Now, the only reason I need a negative t is because from here, we start building our original equation, or the equation we knew we were working towards. We write it in exponential form. We multiply by 4n, and we make n the subject. And this should be very, very familiar, because we found that in part A by putting it directly into the function. So you should be able to do these things in a number of different ways. You should be able to solve for nt by using the logistic equation directly. That was part A. And you should also be able to solve for nt by integrating this, which is clearly quite a process. All right, part D, part C, we can knock them over real quick. Using either a graphics calculator or the program Graphmatica, draw nt. That's what my nt looks like. And using a graphics calculator, determine when the population is maximal. Population is always maximal at half of the limiting population. The limiting population looks like 500 here. Maximal 200 and 250. Whew, that was a long one, but that is how you do worked example 20. You should be fairly well set up now to be able to do question 1, 2, and 3 from that textbook exercise.